In this video, we will show you how to calculate electric potentials from continuous charge distributions. In particular, we will look at electric potentials created by finite line charge and continuous charge distributions on a semicircle. Let's look at our first system. Figure below shows a finite line charge of length A. So that is the system right there, with a uniform linear charge density lambda coulomb per meter. It has a total positive charge of capital Q. Find the electric potential at this point, a distance d away from the right-hand edge of that line charge. The first strategy is to divide the entire line charge into tiny segments and treat that tiny segment as a point charge. So a segment such as that one. Now let's assume that the segment has a length dx and it is situated a distance x from the right-hand edge of that line charge. So the total distance from the point of observation, the point at which we want to calculate the electric potential, would be x plus d. So this is the distance between that little segment and the point of observation. The amount of charge that is contained in that little segment, let's assume to be dq. So the electric potential due to this amount of charge at that point can be written as dV, and that is quite simply k dq over x plus d. So this is the point charge model. We note that the amount of charge dq can be expressed in terms of dx as follows. It is quite simply the linear charge density times dx. So this will give you the amount of charge that is contained within that little element. So the potential created by that tiny element is quite simply k lambda dx over x plus d. In order to determine the potential created by this entire line charge, at point P, we need to integrate that contribution, such contributions dV, from all the elements covering from this point all the way to that point. And that would give us, since k is a constant, it can be taken out, lambda is a constant, it can be taken out of that integral sign, dx over x plus d. Now note, as we cover this entire line charge from this point to that point, the limits of this integral will go from 0 to a. 0 when the element is there, and a when the element is there. So this is a straightforward integral, k lambda natural log of x plus d. Do not forget the limits 0 and a. Now lambda, the linear charge density, can be expressed in terms of total charge as quite simply the total charge divided by the entire length of that line charge, which is a. Now substituting all this information in here and realizing that k is 1 over 4 pi epsilon naught, where epsilon naught is permittivity of vacuum, as we have explained in one of our previous videos, we will get the following for the complete expression for the potential at point P. So V at point P equals kk times lambda is q over 4 pi epsilon naught a times the natural log, substituting the upper limit, that's going to be a plus d, minus natural log, substituting 0 for x, natural log of d. And together, simplifying, we will get the following. Q over 4 pi epsilon naught a natural log a plus d over d. And this is the complete answer for this problem. Problem 2. Figure below shows a finite line charge of length A, right there, with uniform linear charge density lambda. So lambda is in the units of coulombs per meter. It has a total positive charge of Q. Now find the electric potential at point F, a distance h from the origin as shown below. So this right there is point F, a distance h from the origin. We do the similar trick as before. We divide up this entire line charge into very tiny segments. So let's assume that the length of the segment is dx and the position is at a distance x from the origin. Now, the distance between the segment and the point of observation, F, is quite simply, let's call it r, and by Pythagoras' theorem we know r is a square root of h squared plus x squared. So x squared plus h squared, square root of that will give you this diagonal distance. So the contribution to the potential at this point from this element will be, let's call it dV, and it's given by the point charge expression k dq over r. Now what is dq? dq is the amount of charge contained in this element. In terms of dx, it's quite simply the linear charge density lambda times dx. So putting that in here, the potential created by just that tiny element at that point is quite simply k lambda dx over r, where now we know r is h squared plus x squared. Since in principle we can divide up this entire line charge into small elements beginning from the origin all the way to that right-hand side of that line charge, the right-hand edge, the total potential created by this entire line charge can be written quite simply as an integral of this expression dV. And since dV is k lambda, dx, can take k lambda outside their constants, dx, over square root h squared plus x squared. All you have to do is to integrate this expression covering the entire line charge, which means x will run from 0 until a. So 0 is the lower limit, a is the upper limit for the variable x. Now as before, k is 1 over 4 pi epsilon naught, where epsilon naught is permittivity of vacuum, and lambda is the total charge divided by the entire length of that line charge. Now note, as you move along this line charge from 0 to a, as to cover the entire line charge, as you do the integral, this h is a constant. So h is treated to be constant as far as this integral is concerned. Now using the result from standard integral, if let's say you want to solve a standard integral like that, u squared plus alpha squared, where u is the variable of integration and alpha is a constant, the result for such an integral is as follows. So this is the standard integral. Note, in this integral, u is the integration variable and alpha is a constant, and that's the result of integration. So back to the integral for our line charge system. So here, h is like your alpha and x is like your u. Noting the lower limit and upper limit, we can do the integration readily, and that's going to give you the following. So k is 1 over 4 pi epsilon naught, lambda is q over a, and let's put in the result for integration, natural log x plus square root x squared plus h squared. And we have to substitute the limits 0 and a respectively. So let's substitute the limits, and you will get v equals q over 4 pi epsilon naught a. Let's do the upper limit. So that is natural log. X will be a, so that is a plus square root a squared plus h squared. Now the lower limit when x is 0, and that's simply going to be natural log of h. So using the rule of natural logs, you can combine the two terms of natural log, and that's going to be a plus square root a squared plus h squared over h. And this is the complete answer to this problem, namely the potential here due to that system of continuous charge distribution. Next problem, electric charge is distributed uniformly around a semicircle with a radius r. Find the electric potential this charge distribution creates right there at the origin. So as before, let's divide up this entire semicircle into tiny element and treat that element as point charge. So in this case, the length of this element, let's call it dl, and it contains an amount of charge of dq. Let's assume the total charge is positive q. So dq is quite simply the linear charge density. If you assume linear charge density is lambda, so dq is lambda times dl, and lambda is the total charge divided by the entire length of the semicircle, which is pi times the radius dl. So the potential that this amount of charge creates here will follow the point charge expression. So k dq is q over pi r dl over the distance between that charge element and the point of observation is capital R, namely the radius of that semicircular ring. So the potential created by this entire ring at this point can be obtained by simply integrating terms such as that one. And that's going to be quite simply an integral of kq over pi r dl over r. So let's simplify that integral. K is 1 over 4 pi epsilon naught. Let's bring all the constants out. These are all constants. As you move from here to there, r does not change. R is the radius of that semicircular ring. So that is q over 4 pi epsilon naught for k, pi r squared integral of dl. We note that the integral of dl is quite simply the length of that semicircular ring, which is just pi times the radius of that semicircular ring. So this will cancel this pi and one of the r's, which will result in the final answer as follows: 4 pi epsilon naught r. So this is the potential created by this entire semicircular ring at the origin. And that solves this problem. Thanks for watching.